All right, folks, you did it. This is the last video for day 12. I want to show you about a technique for destruct where you do case analysis on a compound expression. So to start with, we'll use this function I've just defined. It's the constant false function on naturals, where it first looks to see if its input is 3, then it looks to see if its input is 5, but in all cases, it returns false. Let's prove that this silly function is in fact the constant false function. Okay, let an n be given. Let's show that silly fun n equals false. So to start with, let's unfold silly fun. Okay, it's got those ifs. Now you might say, well, we just have to keep destructing n, right, to get to see if it was 3, and then we'll keep destructing it to see if it's 5. So we'll need what, at least 6 destructs or something to get all the way through this? Like, oh, that sounds terrible. So there's a trick, an idea. Your proof should ask the same questions that your program asks. So your program is asking, hey, is n equal to 3? So let's have our proof ask that same question. We ask, what is the value of EQB n3? Is it true or is it false? Okay. Wow. Why did that happen? Well, if the cases here are going to be EQB n3 equals true and EQB n3 equals false. And once it has that, Coq's going to automatically, after the destruct, start reducing here. It's going to start simplifying things. But if this evaluates to true, then we get false on the left-hand side right away. So in the first case, we just have to prove false equals false. We're done. Okay, in the next case, okay, the if from before only simplified until the else, right? We simplified to this branch. But we still have to wonder, hey, is n equal to 5? So who knows? Let's keep destructing. We'll ask, is n equal to 5? So destruct, and then notice how the compound expression is in parentheses. We destruct it there. False equals false. Okay, so again, what happened here? Well, this would end up being true. Will be in the n equals 5 case, and we'll return false. Reflexivity, easy. Now, if the n doesn't equal 5 case, then again, we return false. So what would have been 6 or something case analyses we did in 2 by just asking exactly the questions the program was asking. So there's more practical uses of these. So here I'm recapitulating the definitions of LEB, min3, and argmin3. And now I'm asking you to prove some theorems about argmin3 and min3. So the trick here is this theorem you'll prove using some complicated destructs on compound expressions. This theorem, it says corollary, you should be able to get directly from this one, not doing any destructs at all. Okay. So I just wanted to highlight that exercise. There's a couple more things I want to say about this. It's definitely possible to need to keep more information. Okay, so let's try the following proof. Here's a slightly less silly function. It's one that identifies 3 and 5, right? It's a predicate on nats that says true for 3 and 5 and false otherwise. So here's a theorem we might want to prove. If silly fun 1 n is equal to true, then n is odd. Now there are odd numbers for which it returns false, but if it returns true, it was either 3 or 5. Both of those are odd. We're good to go. To do this proof, we'll have to assume for now that EQB gives us correct answers. Let's see. So let's try the proof using what we have so far. So we'll start saying, okay, suppose we have a natural number n. Assume for now that EQB is correct, right? If EQB and m says true, then n and m really are equal. And then suppose we also know that silly fun 1 n is equal to true. We want to show that n is odd. Okay, great. So we'll use unfold in as one of these in tactics. And now let's ask, okay, is n equal to 3? And then, okay, eq simplified, but what happened? What happened to the fact that n was equal to 3? Where did that go? It should be here, right? We're in the case where n is equal to 3. EQB n3 returned true, so I should know, right? Should know that EQB n3 equals true. Where'd it go? It's like, oh, you notice I've gotten really lazy about the EQNs. I didn't use them at all up above. This is the kind of circumstance where keeping track of that EQN is really important. Let's start over. Okay. Now let's ask, hey, what does EQB n3 return? Let's call the equation HEQE3. right? Why not? Maybe HN3 would be a better name, but this is the one we got for now. Oh, nice. So now the equation is kept around. Like, we know that EQBN3 equals true. That is fantastic. Okay, great. So let's see what happens. Why is this poorly indented? Oh, okay. We know that EQBN3 equals true. So what are we going to do? Well, with our assumption that EQB gives correct answers, well, then we can say that just means n equals 3, right? Using this EQB true lemma that we've assumed. Okay, and at that rate, then we can say, well, great, if n is 3, we can replace n below with just 3, and then we know odd B3 will return true. Okay, what about the false case? Okay, EQBN3 is equal to false. We'll remember that. Is n equal to 5? Two cases. Maybe it is. So now we have HEQE5 from this EQN. We say, okay, what happens? And it's the same idea. EQB true lets us turn the EQB into a real equality. Convenient right now. We'll prove that lemma in not too long. Now, knowing that n equals 5, we can replace n with 5, and well, it's true that odd B5 returns true. Great. Aha. Look what happened here. How'd we get here? Well, if you scroll back up to what Silly Fun said, we said we know EQBN3 is false. We know EQBN5 is false. So that means we have to be in this case. But in this theorem, we said Silly Fun 1 n returned true. So what's left after all of those destruct simplifications is false equals true. We get to blow up the world. Okay. I'm going to save these quizzes for one last video. We'll do it separately. I know I said this was the last one, but I think it's going to flow a little better if we treat them separately. Okay, talk to you soon.